All right, so good morning, review session. Okay, so here we go. So this is really depends a lot on you guys. Hopefully you brought your questions. So this is the number one question. What equation sheet are we going to get for the exam? So this is your equation sheet. It has everything that we've ever talked about. It's got all of the standard deviation equations, the pool, the sampling plan. It's got the least squares analysis, definitions of relative standard deviation, the coefficient of variation, percent error, absolute error, how to calculate the mean. Hopefully you can do that. The propagation of uncertainty equations, critical Q values, the Z table for the Grubbs test, P test, F test. So I think that's everything. So that doesn't mean every one of those is going to be used, but I gave you everything so that I have the freedom to pick and choose whatever it is, because I don't want you to run out of time. So I'm not going to, the homework 3 specifically, with all of those calculations and so on, I mean, you really needed Excel to kind of do that stuff accurately. So it won't be some super long calculation like that, because I'm afraid you'd run out of time. So it'll be pieces and bits of those. So given this information, calculate that. Or given this ANOVA table, what's the uncertainty in B or M, or the relative standard deviation? So study those homeworks and be ready to do any one of those little pieces. Okay. So now the ball's in your court. Yes. Okay. Let's go all the way here. Okay, here we are. Okay, yes. So we first had to calculate the limit of quantitation um, in terms of milligrams per liter. And so this was number 19. And so we calculated this value of 37.5, which was calculated by the slope. Well, we had the area, like 10 times the limit of signal, quantitative signal, 10 times that minimum signal was our limit of quantitation in terms of the y-axis. We had to convert that over to the x-axis. So that's what this limit of quantitation would be in milligrams per liter. So that would be the limit. The exogenous amount of GHB in the body was about 0.5 milligrams per liter. And so think about it, it's kind of severe that we wouldn't be confident in our quantitation of that in the blood until the concentration got to 35. So but that way we don't make a mistake and say this person was drugged, when they really weren't. So we don't want to make that false claim. And so we have a pretty stringent limit according to this example. If it's not over 37 and a half, we can't say definitively and be confident that this was a drug situation, that it could have just been natural variability in the body. Well, that's 37.5, but what's our uncertainty in that number? So that's the next calculation. So here we calculated it with this equation. And so this is the propagation of uncertainty that takes two parts. So you have the numerator piece, which is LOQ minus B. And you have to calculate that first and calculate the uncertainty in the numerator. And then you have the quotient. You have the numerator divided by M. And that's a different uncertainty equation, and you have to calculate then this uncertainty in that. So these are the steps that you would go through. So we'll just call that numerator over M. And so this is the calculation for the numerator. It's that difference. And each one of those pieces has uncertainty in it associated with it. So this is a sum and difference, and so we use the squares of the standard deviation. So the variances, we add those together. So this is the numerator value, 22,748 area counts. And so what's our S-num? S-num is the variances added together, and you take the square root. So in previous parts of this homework, we had calculated the uncertainty in the LOQ and the uncertainty in the intercept. So this is that LOQ was 10 times the blank value, 267, and so that would be that 2670. And then the 194 was out of the ANOVA table for B. And so that's 2673. So that's the uncertainty in the numerator. Okay. Now we can use that in this quotient piece. So we have two parts there. So it's the RSD of the numerator squared plus the RSD of m squared. Take the square root and multiply by x minimum quantifiable, x min cube. And so these are the numbers. So this was the uncertainty in the numerator. This was the numerator value. And then this was from that ANOVA table for M and SM. And so we end up with 4.4 milligrams per liter. Would be the uncertainty in that 37.5. So that was at the end of a long set of calculations. So good job getting there without missing anything until the last one. Oh, oh yeah, I got you. Yeah, 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 sure. I'm glad you identified which part was the error. Yeah, that's good. I figured out what was wrong with the Blackboard. It wasn't showing you your grades after you submit your grades, and it was because these questions related to, oh boy, where is it? This one. These grades were entered in as essay instead of like multiple choice. So if they had been entered as multiple choice where you select A, B, C, D, or E, then it would have been automatically graded. But somehow when I transferred the quiz from my quiz maker, TestGen, over to Blackboard, these got put in as essay questions. And so it was waiting for me to grade them. And so I just went through on these 4 or 5, just gave everybody credit automatically on those. So make sure you got the right answer. So let's go through these just again, just to make sure you got the right answer, because it, no matter what you put in the text box, it gave you credit just so that you would get your grade and you would get which ones you missed and which ones you got right on all of the others. Okay. So where do you look to see if the data is normally distributed? It says right up here the normality test. So that Anderson-Darling normality test, that would be the answer A, would tell you if it's normally distributed. So the null hypothesis is what for this particular thing? Yes, it's a test to see if the data is normally distributed. Okay. And so the null hypothesis would be it is a normal distribution. And then this is the probability that that's true. Okay. So, and it's above zero point 0. I know it's kind of pixelated, but it's above 0.05. So we would say, yes, we're not able to reject that it's normal. It may not look exactly normal, but we're not able to reject that null hypothesis that it's normal. Okay. Okay, number 23. Where does one look to determine if the data tails to the right or to the left? So which of these values, you have the mean, the standard deviation, the variance, the skewness, the kurtosis, and then the median quartiles, all of those things. So which one talks about tailing data? Skew, very good. So that would be B. So here's the other one. Where does one see if there's an outlier in the data set? I went ahead and picked this. You would look at the histogram area, not the Instagram area, the histogram area. And here's E. It doesn't show an asterisk. A lot of times the Minitab will put an asterisk if it doesn't. It does a outlier test automatically and will show you an asterisk. But that's where you would look up here in this data panel. Okay. Look in the above figure. How many data points were there in this study? Well, you can see here, here's N, and it's 10. Okay. How many degrees of freedom are left after computing the mean? So N minus 1, so 9. So this is N minus 1. And then refer to the above figure. The smoothed curve on top of the histogram is the blank distribution function. The Gaussian, yes. These are all of these others are legitimate distributions, but we in this course have just only been using the Gaussian distribution function. The only other one I've really come across that I had to use, well, I've had to use two others. The Poisson distribution is for rates, like counts per second is for radioactivity detecting, because I worked at a nuclear plant. And so we had to use the Poisson distribution when we were dealing with background radiation counts. And we're trying to determine if this was statistically significantly above background radiation. So you could count for long periods of time and make a histogram of your readings in terms of radiation counts per minute or counts per second, or millirem per minute, or what have you. But anytime you have a this per that, a fraction or a ratio, often, I don't want to say always, but often it will follow the Poisson distribution. So that's all we're going to say about that. That's when you would use that one. And then when you're sampling things and not replacing them and so on, you can use a hypergeometric function for small data sets. And so we're not going to get into that. Okay. So what other questions do you have? 16? On number 4? Okay. Okay, so let's see. And so here we're trying to calculate the uncertainty in the GCMS signal from the 0.5 milligrams per liter. Okay, so we've done this new regression. I've gone back a little bit just to set it up. Okay, new regression analysis. We've got better standards and so on. And so look, our p-values are good here. They're both below 0.05. And so we can use both M and B in our model. So we calculate the area counts, the Y signal, if this is Y up here and this is X down here, the Y signal that would come from the amount of GHB already in the body. So this would be the 2494 area counts for the baseline amount. If we did, the body's natural amount of GHB. So that was number 15. So now 16, what's the plus or minus on that? What's, the 2494 plus or minus what? So that's the uncertainty. So here we are with this equation, mx and b. So we have, again, a combination. We've got a multiplication, which uses one propagation of uncertainty scheme, and then we've got an addition, which uses a different propagation of uncertainty scheme. So we've got to do it in parts. Now, just like you do in your calculator, if you're going to do this equation, what's the first operation you do? You do m times b, right? M times b, and you get a number, and then you add, you do the multiplication, m times x, and you get your result, and then you add b. So you do that in two parts too. So we'll do the mx part first, and then we'll do the plus b part. So this is the mx uncertainty, and we can go to our ANOVA table and get those values. Let's see, where's our ANOVA table? Here it is. So the M uncertainty is that 3.4. You see where it came from the table here? Here's SM, and here's M, and then here's SB and B. Okay. And then we have the X. We're told right here this 0.05, this 0.5 with a 3 in parentheses. That's 0.5 plus or minus 0.3 milligrams per liter. You see how to read the uncertainty when it's in parentheses? That's another skill. And so that's our SX, and this is our X. And we got our SM over M. We take those ratios, those are the relative standard deviations, we square them, add them, take the square root, and then we multiply by M and X. And we get our S for the product of MX. So that's the uncertainty for that first piece. Here's our value, 182. And so then for the final result, we have mx plus b. So we have the smx, which we just calculated, squared. And then we have the SB from the table, 194 goes right here, squared, take the square root, and that gives us our SY. So that's the 267 that we have. So that's the uncertainty on the y-axis. We have the counts from our endogenous amount of GHB, and then our uncertainty because of the 0.3. Our bodies naturally produce 0.5 plus or minus 0.3, so we have an uncertainty on that y value of 267 area counts, which sounds like a lot. I mean, it's about 10%. Let's see, what was the answer? It was 2494. So yeah, and then our uncertainty is 267. So it's a little bit higher than 10% plus or minus on that y-axis. And then 19 and 20, we take those and put them over on the x-axis, and we get 37.5 milligrams per liter is our base value in terms of the quantifiable amount, plus or minus 4.4. If y'all can do this, and if you get comfortable, let yourself get it. If you get comfortable with doing these two-step propagation of uncertainty calculations, you're really going to be valuable. I mean, I was at Pantex. They had around 3,000 employees. We had 300 or so scientists and engineers. Smart group. And there was a handful of us, maybe 5 out of 300, that could do this. Now, I'm sure that the others could learn it, but they hadn't done it regularly. And so they weren't comfortable with it. So being able to propagate your uncertainty and calculate those uncertainty values is a super skill. Yeah. So anybody can remember vocabulary. Okay. But this is the stuff that will set you apart. So you want to be able to do it. Mm-hmm. As long as you know what the order of operations they're in? Yes. Yeah. So you just take the order of operations, like we have a MX and a B, and you know you have two steps because you've got a mixture. You got a multiplication piece and an addition piece. So just like you do the order of operations, you're going to multiply MX first. So you calculate that value and calculate the uncertainty in that value. Then you can use it in the addition piece. So this is it right here in both steps. I have a video on the forensic page, maybe a couple of years back, where we did the quadratic equation. It's a beast. It takes up the whole board. I was just doing it on the board. And so, because think of how many steps. You know, you've got the square, and you've got the plus or minus, and the square root, and the minus, you know, I can't remember it again. I have to sing the song. But, yes, 20? Yeah. So it'll be on the video. So we did it just a minute ago. Yeah. So we went from this one and then did, yeah, we did 20. Let's see, let's see, go back to this one. I want to compliment you on bringing forward the error, finding the error that the T inverse here should be alpha, not alpha over 2. Okay? And so I went through and changed that number and then regraded and fixed that. But it's 4.303 is the 95% confidence p-value. So thank you for bringing that to my attention. Was a perfect email sort of pointing out an error. I think this is this, and here's why. And there was lots of evidence why. Like, here's a screenshot of a t-table. Here's what we see, and so on. And I was like, okay, I'm convinced. And then I did some research on my own. I was like, yeah, absolutely, that's right. So we don't divide alpha by 2 using this formula here. It's 0.05, and then with degrees of freedom was 2 because we had 3 data points. And so our t-value should be 4.303. So in line with my promises that I'm not afraid to be pointed out when I'm wrong, you get a sticker. Which one you want? Yeah. Okay. So, yeah. So we'll get. Oh, it does. Okay. I'll look into that. Yeah, let's see. Thank you. I'm a bit alarmed that that error had been on the homework for 3 years and no one else had picked up on it. Yeah. So, so if you get it wrong, sometimes do your research. You might get a sticker. I had a student point that out. I had an error in PChem on this one particular problem in the class, in the lecture notes, and it had been there for 3 or 4 years, maybe 5 years. I don't know how long the error was there. And it was not on the exam, so the student on Friday afternoon after a PChem exam was redoing that problem in the notes just because she just, it was bugging her. She wasn't getting the answer that I had, and she finally proved to herself, this is a mistake. There's right here is the mistake. She pointed it out to me. And I wrote her a really good letter of recommendation because I said, here's a student, the question wasn't even on the Friday exam, and it still bothered her. And so Friday afternoon, when everybody else's exam's over, where they're out doing whatever they do, and she's working a PChem problem to try to figure it out, and she found an error. So I typed that in there a second. So hire her. And I hired her as TA the next year. Yes, Jesse. Mm-hmm. It's because that parenthesis replaces the previous place value. And so you could do it like this, 15.9742. Um, that that 2 in parentheses goes right here. So you could just draw a line like that and you could say it's 0.0002. So wherever it's next to, it replaces that. So that's correct. And sometimes you'll see two places. So if we did 15.9742 and in parentheses we had 2, 1. Okay, let's draw the line right there at the parenthesis and let's put 21 right here. And then you fill up the zeros to the decimal place. So whatever's in parentheses is the previous digit or digits of uncertainty, and it just tells you the place value. So it's a very concise way to write your uncertainties. And so that's, you know, humans are lazy and scientists and engineers are human, so they're going to use the shortest possible way to notate things. If you don't know the language, then you won't be able to pick up on it. So this is the language of uncertainty, one of the shortcuts. Yeah, yeah. And that's super critical because if you're going to propagate the uncertainties and you start with something wrong, you start at the wrong place, you're going to end up at the wrong place. Yeah. Yes. Book material. Ah, yes, yes, yes. Okay, so this is the tricky one here is it looks like you just have one uncertainty, right? And so you have, but every mass measurement, you have the tare mass, right? So you have your balance, right? And you put your container on there, and that's one measurement. And then you put the stuff in there, and that's the second measurement. So every measurement has two uncertainties in it. You have uncertainty in the zero and uncertainty in whatever you're measuring. Both those uncertainties are 0.5. And so uh, S total, I mean, let's just look at the equation. So Y would equal mass tear, oh no, mass minus mass tear. So let's do that. Come on, where's my eraser? Okay. So that's the container mass or whatever it is you know you're canceling out so that you can get the difference between those two. So each one of those uh, SM is equal to plus or minus zero point 0.5 grams. So SY is equal to square root of SM squared plus the square root of S plus the SM tear squared. So whenever you're taking like a burette reading, when it's 0.05 mils, or mass readings, when it's zero point 0.5 grams or 0.0002 grams, or whatever it is, whatever that uncertainty is for your reading, you square it and you double that because you're taking two readings, you're taking differences. So it's always 2 times that uncertainty squared, and then you take the square root. And it should be something like 0.07 or something like that, zero point 0.7. I don't know, let me do it on my calculator. Yep, zero point 0.7. So you see, it's not 0.5, it's a little bit higher. It's 0.7 because you're uncertain in your tear mass and you're uncertain in the mass that you're after, the total mass. Hmm. I think I try to do 50 so that we cover everything and there are only 2 points apiece. Yeah. Scantron, yeah, so I can run them through, yeah, real quickly. So I'll spend my time ahead of the exam trying to make a really good exam so that we can do a Scantron and I can grade them really quickly and typically get the grades out within a like within 24 hours. Yeah. So I like people to know where they stand in the course. And after studying, you have an exam, bang, you're really motivated to know how well did I do? I can't stand it when you have to wait 2 weeks. It just you just lose something there. I will go through. It'll take me actually. It might take me 2 days or so because I like to then update all the attendance and put that in there. Update all the homeworks, put that in there, so then I can come up with a tentative letter grade. So you have your exam, your homework to this point. I'll do a data audit on the control charts to make sure everybody's entering their data, and then so you'll have a little bit of each of the pieces, a little bit of homework grade, a little bit of control chart grade, your attendance, and your exam. Attendance is going to be, because it's rare that people have already missed their 3 plus a few more at this point in the course, so your attendance grade will probably be all hundreds, hopefully. Your homeworks too will be very, very high. And so if you do poorly on the exam, those other things will pull that up a little bit. So look at the exam grade, learn from your mistakes, but the homework and the control chart and all of that stuff will give you some help. Just don't get complacent. Okay. Yes. Mm-hmm. Oh, Yeah, so we look at like from our calculator or from Excel or whatever in our uncertainty, we've got all these digits of uncertainty. And so I would say you can keep one or two non-zero digits, right? So we're not interested in this, leading zeros because that's just telling you where the decimal place is. So we're either going to round this up to 3.03 or 2.6, round it up to round that 5 up to a 6. So we could write this in 2.6, 0.026 or 0.03. So those would be the two acceptable ways to report that uncertainty. Now, that tells us where to round. So if we chose, so we choose the uncertainty first. Let's say we wanted to do the 0.03. That tells me I need to round this number at the hundredths place. They have to match. 23.03 plus or minus 0.03. So that one would be an acceptable answer. Okay. What if I use the other one? I'm going to choose it first. I'm going to 0.026 plus or minus. So if I choose to keep two non-zero digits of uncertainty, then that tells me I need to round in the third decimal place. Okay, so since I'm keeping 3 decimal places in my uncertainty, I need to keep 3 decimal places in my y value. So 23.036. 036. And so either one of those would be acceptable. And so this one here, this one's keeping 3 digits of uncertainty, so I'm going to mark that out. So it's not that one because that's keeping too many digits of uncertainty. This one, oh, I guess I should round that to a 4 instead of a 3 because that's a 5 in the next, yeah, so 23.04 would be that. And so that one is found right here. So that's good. This one has 2 digits of uncertainty. It didn't round up to 2.6, and also this has four decimal places. This has 3 decimal places, and so those don't match. And this is a mismatch. The first one is a mismatch. So both of those, the number of decimal places in the result and in the uncertainty don't match, and so that's why they're out. Okay. This would be the other answer that I could accept. And so if I'm looking at this problem and I'm lazy and I'm trying to make a quick exam and so on, then I might include that one as an answer and delete that one. So if they're both acceptable, you need to recognize, okay, the decimal places have to match. These right here match these right here, okay, or those and those. Everything's rounded correctly, the 0.04, 0.036, okay, yeah. And again, it's about communication and about trust. If you mess this up and you're communicating to someone else, it's not a egregious error, okay, but it's a little sloppy, right? If you contain like 4, decimal places after the 23, and your uncertainty only has 3 decimal places, you could actually create an error where they're going to see that and they might assume that the 25 is in the third and fourth decimal place, but it's really in the second and third. Like you might actually cause someone else to make a mistake because you didn't match up your numbers. Or they may just doubt that you wrote it down right. Like if I looked at that, I would say, wow, my question is, did they lose a zero? Did they make a mistake here? It's confusing me. And so you don't want to produce confusing results. So they should match. Seems silly, but it's important. I say that we should never include 3, but I think sometimes some of the physical constants in NIST. Let me see if I can find them. So here we have, let's, Avogadro constant. They don't have it. I mean, they have got the constant, but sometimes they, let's see, definition of uncertainty. Sometimes they list it. I guess this is a definitional. Let's see, go to new search. Um, let's do electron mass. Okay, see, they list the concise form with the 2-8. So they're keeping 2 digits. But I think I've seen it where they have 3. And so they're kind of breaking my rule, but they're using it in parentheses, and it would just replace the previous 3. So even though I say no one ever shows 3 digits of uncertainty, I have seen it, but it's rare. Yeah. Okay. Planck's constant. Let's see. Ah, it's defined also. That's Boltzmann. Yeah. Yeah, it might be. Trying to search. Boltzmann constant. Exact. These are some good things. So that they're defined. The masses are not defined though. Let's see, kilogram. See if it's defined in something else. Anyway, but you can see the uncertainty. I didn't find any examples where there's 3 digits. It's rare. That's my point, right? Okay. Yes. Describe some of the questions. Oh yes, yes. This the Let's go on to that one. Come on now. This one? Yes. Okay. So yeah, any questions about these or like the control chart or anything or the dendrogram? Yeah, for sure. Like on this one, which are the 2 closest points? 2 and 10. That's right. It should be easy to see. Those are the first 2 to join together, so they're closest to each other. Yep. True or false? Dendrograms are limited to data of 3 dimensions. Why do you say false? Scatter plots limited to 3 dimensions. Yes, but this could be limited also to 3 dimensions. But you're correct. But why else would it say? Um, yeah. So remember, the distance calculation is the this data point minus the x of this data point minus the x of that data point squared, plus the y of the 2 data points squared, plus the z of the 2 data points squared, plus the u, whatever dimension that is, different squared, plus the t of those 2 data points squared. So it's unlimited in the number of dimensions. So this is one of the most powerful data reduction techniques because you could have 30 dimensions of data. What kind of possible sample would have 30 dimensions? Think of a drug cocktail, right? It's concentration of cocaine, it's concentration of meth, it's concentration of this. What if it's a waste bucket in a drug lab? Was the waste bucket in this drug lab the same as the waste bucket in that drug? Were they making the same stuff? Whatever. You could have 30 different compounds in there. Okay. And you've got all these different samples. Well, you could do the difference in all 30 compounds and compute the different distance between those 2 samples and plot it on here. So You have all your samples listed on the x-axis, and the y-axis is just the distance between all 30 of those dimensions. And then you would find the two waste buckets that were closest to each other in concentration. Very far-fetched example, but trying to get a conceptual idea of what multiple dimensions would be. We think when we hear the word dimension that we're talking about spatial dimensions, X, Y, and Z, but it's any numerical thing. It could be the concentration of drugs 1 through 30. Those are all different dimensions because they can all be independent of each other. Yeah. Nice. And then if I were to define, okay, how many clusters are there if we define our cluster difference as point, we'll say 0.5. So here's 0.5. Draw that line across. And we've got, however many things hit. So we've got one grouping of 2, one grouping of 3, another grouping of 2, a single point here, and a grouping of 2. So we would have 5 distinct groups if we defined anything further apart than 0.5 as a distinct group. Okay. If we made it 0.65 or whatever, we come across, and now we've seen some joinings, right? We've got an outlier here, this unique person or data set, and then we've got a group here, a couple of pairs that are groups, and then we've got a big cluster here which contains 1, 2, 3, 4, 5. So a group of 5 here, 5, a group of 2, a group of 1, and a group of 2. So those are our different sizes of groups. But you have to define the distance that you're going to use to declare what a group is. To be unambiguous, yeah. Yes. No, an outlier screws it up. So the standard deviation is how scattered the data is. And so if you have a situation like this, it's going to make the standard deviation larger than if I got rid of it. So if I had 4 data points close together, I'd have a tight standard deviation. If that data point was over here, there would be a bigger standard deviation. So the standard deviation is just the deviation from the mean. So wherever the mean is, it's the distance from each of those data points from the mean squared, added together, and divided by the number of data points. Take the square root to get it back out of squared space and back down. And so the more the data points differ from the mean, the more standard deviation you're going to have. Yeah. So outliers mess up your uncertainty prediction. So like in this case, this outlier really messes up the standard deviations because these limits, look how far apart they are from the data. If we got rid of that outlier, our standard deviation would probably be something like this, because it wouldn't be averaging in that outlier and making those standard deviation bars wide. So this is why in your training period, if you have a really bad outlier, then it may make sense to not use it because it's just going to push your limits out so far that you'll never ever understand the true variability of your data, and you'll never have anything go out of control typically because your standard deviation is not right. Yeah. But if you do, and the reason I say this is a really bad outlier is because it's not just across the line, it's way past the line. So that means that all of this data is really drawing, so this data is drawing this line in, this data point is pulling this line out. And so they're pulling on that line. And because we have so much data in the middle, it's really pulling those lines in, and so that's why this one is so far out. You could do the z-test on that. Z-test, which would be that data point. So we'll call this, we'll call it x question mark like we did in the notes. So we have x question mark minus mu divided by sigma. Okay, and then we could look that up in the z table and see what the what we're seeing is, let's say it ends up being like 3. Okay, that means you're 3 sigmas away from the mean. When you're, let's see, when you're 1.96 sigmas away from the mean, so almost 2 sigmas away from the mean, you're you have a 97.5% chance of being below that point, right? If you go beyond 1.96 sigmas, now you have less than a 2.5% chance of being, just barely past that line. If you're 3 sigmas away, you have like a 0.001% chance. So there's one chance out of 1,000 that this data point is from random noise. So that's why we would call it a true, bad outlier, because it's so improbable that it would be that high without some special error causing it to kick off like that. Yeah. So if that happens in your training set, then you just need to make a note of it, take that data point out of the calculation of your mean and standard deviation, and like I said, make a note of it, and then use the 16th data point. So you'll have 15 data points that you'll average for your standard deviation and your mean, but you will have thrown that outlier out. And that's if it's way past 1.96. If you've got an outlier that's, you do this z calculation and it's 1.98 or 2 or 2.1, go ahead and keep it, because there's a 2.5% chance that you would get that data point, even though nothing special has happened. Yeah. Yes. Really? Hmm. There's anything special happening this Thursday. We'll grab this over here. Yeah. Yeah. I don't even see it in my. Hmm. No, I don't. I just don't see it even on my computer. I will. I will share like last year's version and put it on this year's playlist. That way, yeah. That way you have it. Something may have happened. Yeah. Oh, was that the one that I did? Was my laptop not here? Yes, that's right. The video was awful. Yeah, so that Zoom, I used a Zoom to record it, and this mic and everything just didn't. I probably should have used the lapel mic, and it was a mess. Yeah, so that's what happened. That's why I don't have a copy of it. Okay, I'm gonna write myself a note. I thought I did that already, so it's not on the playlist. Is it? Okay, I thought I did it. I thought I brought in last year's and put it on the playlist. Okay, good. Are you ready? Yes.
the Z test, the T test, and like the F test gonna be?
Mhm.
Do we need the tables or are we just gonna, or is it gonna be just?
I'll show you. So we got small versions of them. Yeah, so here's the critical T for alpha, and here's the F upper and lower. So those things that you would have to look up are already here. And so you just need to know, like, if you have to calculate the T experimental, then you compare it to the T critical, right? And so which way does it go? Like, first of all, what's the null hypothesis for the T test? It's in the name. Yeah. So the means are equal. So same mean. Okay. And then we have an if-then statement. If T exp is greater than T critical, then what? Reject. Then reject H0. Now this one is a little different. The two-tailed F test, equal variance. Got to know what variance means. That means uncertainty. So do they have the same uncertainty? And this one, F experimental, is between F low and F high, upper and lower. Okay. And so if this is true, right, if experimental is inside those limits, then the null hypothesis is great. If F is outside those limits, either it's higher than the upper one or lower than the lower one, then you reject HO. So if F experimental is outside limits, then move up here, reject HO. Now, why do we have an upper and a lower limit? It's because, well, I don't know what S1 and S2 are. Right? I've got two data sets. And if I pick, like, let's say S1 is larger than S2 and I square them, a squared number that's larger is larger than a squared number that's smaller. And so my F number is big. So I'm really pushing it against the upper F value. So if it's higher than 35 in this case, 39 in this case, then it would be not equal variances. We would reject H0. But what if I just, because I'm defining 1 and 2, 2 is larger. Like if I just defined it in the opposite way, then my large number would be in the denominator and my small number would be in the numerator. And so then I would be pushing against the lower F value. So this F test is versatile. It doesn't define which one is on top or below bottom of that ratio. We're just taking the ratio of the variances and testing if it's close to 1. If I picked the big one for the top, then I'm testing it against the upper F value. If I pick the big one for the bottom, then I'm testing it against the lower F value. So that's all that's going on. That's why we have limits that are, the middle is good, it's close to 1. The limits are bad. If I get outside either limit, then they're not equal variances. So they don't have the same standard deviation. They're significantly different. We saw that in the trainee was big and the forensic chemist was narrow. And so it allows me, this test, to put the trainee on top and the forensic chemist on bottom or vice versa. This way it would give me a positive big number, and the other way would be less than 1, really small. Yes. Mm-hmm. Yeah, I messed that up with the t-test, right? And so you have to make sure that you're doing it right. So for the t-test, we don't do the alpha over two, but for the f-test, we're testing each tail individually. And so in those cases, since we're really specific, is it the upper tail or the lower tail, then we divide it by 1/2. And it would be 0.025 for the top number and 0.025 for the small number. And these are for n equals 3, and so that's what I'm telling you too. Like, I'm not going to give you then a problem on the test where it's n equals 5, because it wouldn't apply, So plus, 3 is the sweet spot, right? You need 3 data points. You can have 2 close and an outlier, or you can have them all. Adding 4 or 5, 6 points is busy work after that point. You can get the concept across with 3 data points. Yeah, it's 9 o'clock. Got 15 whole more minutes. Y'all let me know when you're done. Yes.
Would there be like Excel stuff exam?
Output, like ANOVA output. Yeah, but not, yeah. I
Oh, not like
wish. Oh no, like
okay.
which formula do you use?
Yeah.
Yeah. I hadn't thought about those types of questions. I guess I could, but yeah. STDEVP versus S, you might be able to figure some of those out, but no, I wouldn't do that. Go ahead. Yes, good. So yeah, so H0, the null hypothesis, is not an outlier. Golly, my handwriting is so bad. Okay. So you need to know that. And so then if Z XP is greater than, there's no space. So if your experimental value that you calculate is greater than your critical value, then reject the HO. And the same for the Q. So again, if experimental is greater than Q, critical, then reject the null hypothesis that it's not an outlier. So it's a double negative. It's not an outlier. Therefore, it is. Okay. I I could. The reason I'm hesitant is because to make a good one where it's not going to be like, if I make a mistake in coming up with a problem on the fly, it will really confuse people. So that's the reason I'm reluctant. I could probably do it. Before we do that though, y'all haven't asked me any questions about the sampling plan. Are you completely comfortable with that? Silence. Okay. So if we have, let me do a quick question on the sampling plan, and then I'll try to do a. So let's say 1,200 bags, and it was 800 blue and 400 green. What's your sampling plan? So how many blues would you do? So down here, the sampling plan is 20 plus 10% of the amount minus 20. Okay. So we're going to take 20 out of 800. So we have 780 left. Everybody see? And then we take 10% of that times 0.1 is equal to 78. So 78 plus 20 is 98. 98 blue bags would be tested out of that 800. So you'd think, man, 98, that's a lot of samples, but you have 800. So we're not even close to testing all 800. So 98 is way better than testing all 800. You would pick them randomly from that. Now let's do the green. So 400 minus 20, we get 380 times 0.1 gives us 38. So 38 plus the 20 equals 58 bags of the green. So that's not too bad, the sampling plan. You just got to work through your plan. It's a very conservative plan. You're testing a lot, maybe a few more than you need to, but you're still saving a lot of time by not testing. In this case, if you were to test, I don't know, 20% of them, that would be 240. We're coming in under that. If we were testing 10% of them, that'd be 120, and we're coming in a little above that, 98 plus 58. So of the 1,200 samples, we're testing more than 120 because we have two different lots in there. 10% would be 80 plus 40, which again would be 120, yeah. So we're testing a little bit more than that because 10% may not be enough. Yes. Yes, it's because it's bigger. So because our denominator is smaller, we're doing n minus 1 in the denominator, then it makes our standard deviation a little bigger. And that's why it's conservative, because you're trying to communicate your uncertainty, but you want to be sure about that. And so make it a little bit bigger to kind of hedge your bets. And so for a sample, we're giving the bigger number, not the smaller number. Yeah. So the examples I would give for the propagation of uncertainty would just be these examples that are here in the notes. So, like this case, um, this is, in the video I could change the numbers, but it wouldn't change what we did really. And so, I guess the thing that's key is being able to find your uncertainties in the ANOVA table. Here they are, okay? And this is M and B. And once you have those, and then once you have the uncertainty in your X value right there, then you just do it in pieces like I'd walked through. So we do the numerator, we do the MX piece, we calculate its uncertainty, and then we would do the addition piece and calculate its uncertainty, and then and so then we would have the total. Yeah. We had the one where we solve for x, yeah, right here. So this is the reverse of that situation. Now we're solving for x. So this is where we have the numerator and the denominator. So again, if we're doing order of operations, if I have a mathematical equation that's two numbers, difference between two numbers, and then a division, I'm going to do the difference first, and then I'm going to divide by m. Just like that's how I would do it on my calculator. So I'm going to follow the same steps for the uncertainty. So I'm going to do the uncertainty in the numerator first, and then do the division uncertainty. So that I'm just going to call that numerator piece numerator and solve for the numerator. And then I'm going to calculate the uncertainty in the numerator. So this is the sums of the variances. Take the square root. And then I can do the division piece. So I have the numerator divided by m, and so those are the RSDs of the numerator and the RSDs of the m. Square them, take the square root, and then multiply by the value that I'm calculating. So then that gives me the uncertainty in the x value. So those are the two possible ways for a simple linear equation, y equals mx plus b. We can calculate the uncertainty in y. We have three things that go into it. We have the uncertainty in m, the uncertainty in x, and the uncertainty in b. How do all three of those fit together? We do the multiplication and then the addition, and then we get the uncertainty in the result, y. But sometimes I need to solve for x. So I move b over, subtract it from y, and divide by m. That's this equation. And you have the reverse of those. You've got to do the division, the multiplication, the subtraction first in the numerator, calculate the uncertainty there, and then do the division piece and calculate the uncertainty. So it just, based on the order of operations you do in calculating the problem, that's the order you do in the uncertainty analysis. So hopefully that was good. Mm-hmm. Yeah, so the one in class I had three y values, and we took an average and a standard deviation of the three y values, and then we solved for the x mean and standard deviation. So that was, yeah, but those the three y values. So in class I had three area counts, right? And I took those and I made an average and a standard deviation. Well, that's this number right there, and that's this number right there. So I just didn't show the three values that went into this number, or however many there are, to get the endogenous GHB concentration. So that is the, I guess, disambiguation. And from the in-class thing, I had the actual three discrete y values that I measured, got their area counts, computed a mean and a standard deviation, and then did the propagation of uncertainty. So this, we're given the mean and standard deviation at the 0.5 plus or minus 0.3. And so then it figures in. Yeah, yeah. That's a good question, actually. That's a perfect question in the sense that we drilled down until we got to the thing that confused you instead of just the procedure. Yeah, so that's what I really would like y'all's questions to be. And those are the kinds of things I can answer by email real quick. You know, if you say, look, I don't know where these three numbers came from. I was like, okay, I was doing this and that. And in class, those are the more useful questions too. Rather than watching me do the same procedure over and over again, that doesn't build confidence. Actually drilling down to the thing that tripped you up, that's even better. Yeah. I like me doing problems on the board is very much like a basketball team watching their coach shoot free throws. When it comes game time, you've not got the muscle memory, you know. You're like, oh, that looks easy. I could do that. So it just doesn't generate the muscle memory. All right, let's go do it.